NASA Langley. My name is Eric Gillard from NASA Langley Research Center, and we'd like to welcome you to historic and hot Hampton, Virginia, the site of an Orion water drop test. It's the 9th such drop test that we've done so far. So I want to give, before we continue on with this, we want you to hear from you. What questions do you want to ask us? So we have a guest, so please make sure to ask us any questions, and we will make sure that our guests will be able to answer them. So before we get to our special guest, I want to give you a little bit of a brief overview of what you're going to see with the Orion capsule. The Orion has been undergoing a series of water impact tests in NASA's Hydro Impact Basin to help engineers understand how to best protect the crew and spacecraft when they return to Earth from deep space missions. The test capsule, coupled with the heat shield from Orion's first space flight, will swing like a pendulum into NASA's 20-foot deep basin from the gantry. The gantry is a 240-foot high, 400-foot long, 206-foot wide A-frame steel structure. It was built in 1963 and became operational 2 years later. The gantry allowed astronauts like Neil Armstrong and Edwin Buzz Aldrin to train for Apollo 11's final 150 feet before landing on the moon. Inside the capsule will be two anthropomorphic test dummies, one representing a 105-pound woman and the other a 225-pound man, outfitted in spacesuits equipped with sensors. These sensors will provide critical data that will help NASA understand the forces crew members could experience when they splash down into the ocean. Water impact testing is helping NASA evaluate how the Orion spacecraft may behave landing under its parachutes in different wind conditions and wave heights. During Orion's next test flight, Exploration Mission 1, the uncrewed spacecraft will launch on NASA's Space Launch System rocket, travel more than 40,000 miles beyond the moon, and return at speeds of up to 25,000 miles per hour. So, this is an overview of what you're going to see. I'd like to bring in my special guest. His name is Mark Baldwin. He's a crew analyst with Lockheed Martin. Thank you so much for joining us today.
Sure thing.
So, how many of you these water drop tests have you been involved with?
So from the beginning, Lockheed Martin and NASA have been constructing what you see here. This is 3 years in the making.
Nice.
Not just the tests themselves, but what's inside.
Okay.
It may look like just an exterior structure, but inside is packed with sensors. We do have 2 seats, 2 suited dummies, to measure really the impact loads on the crew during an impact like this.
Okay. So what do you hope to see? Obviously, you want to see a big capsule make a big splashdown, but
Yeah.
what do you hope to see behind the scenes, and what kind of data do you hope to collect?
Right, so I'm part of a small group of landing analysts and occupant protection analysts that will reconstruct what you see here. So we expect it to kind of go into the water, dive to a certain depth, pop back up, create a pretty good splash for the crowd here, and then settle back into the net that's over there. This is part of a continuum of types of tests we're running to really characterize what's going to happen in all types of scenarios, really the extremal scenarios that we could see when we splash down either in the Atlantic or the Pacific.
Mm-hmm. So is this pretty kind of much old hat for you? I mean, you've seen so many of these things before.
No.
It's like,
No, everyone actually has a unique purpose. This is the 9th of 10 tests.
Right.
You could say, why are you running 10 tests? Why not run 100 tests? Why not run 2 tests? Well, every one actually is a data point that we're using to fill in our understanding of what happens.
Mm-hmm.
So the conditions here are set unique to a situation that we could experience in the Pacific. So on Apollo 15, they lost a parachute. And when you lose a parachute, something happens. You begin to swing like a pendulum underneath the chutes. Well, through interdisciplinary work, in analysis with the guided navigation and control guys, the landing guys, the structures guys, we came up with a scheme that said, if that happens, the best thing you can do to lower the loads on the structure and on the crew is actually turn yourself sideways. So that's why it's actually oriented the way it is. So if you look at it, the feet of the crew are actually pointed that way. Normally, they point in the direction you're traveling. So this is going to be beneficial to give us lateral loading into the seats and into the structure, and that's what I mean by a data point that's kind of at that, but it's still based in a real life situation.
Right, you said this is the 9th of 10 tests. So what are you trying to build from test after test after test, the previous test, to this one?
Yeah, so you can see some of the tests that were actually done on YouTube. We changed the attitude of the vehicle, we changed the velocity of the vehicle, and we really see a different response of the vehicle through the water. When we have interior cameras looking at the dummies, we actually see how that translates to loads inside the capsule, at the seat, in the suit, And our job is to make sure we can keep the crew safe. And we do that. You mentioned the crash test dummies. We have lots of sensors built in. And this is what they do in automotive. Your cars are designed the same way, where we measure things at the neck, accelerations in the head. Those types of outputs will give us a sense of how severe what you see externally will be on the body internally.
Okay. So my next question for you is, what is the best part of what you do at Lockheed Martin involved in NASA Langley's expeditions and journey to Mars?
So it's really a combination of working with many different teams. So to get this done, there was interaction from the landing group, which I'm part of, the Langley folks, which conduct the tests, the structures teams. We built this test article and put it together. We also, since we have the suits in there and the seats, we had to work with the Johnson Space Center suit group, the crew survivability guys. We have the crew systems guys that design and built the seats. And then one of the unique things about this design is we have an impact attenuation system that's custom tailored to every crew member that gets inside. That is a mechanism that we've put in place in this test series to see if it's operating the way we expected.
Okay. So
a lot of interaction keeps you on your toes because you don't know who's going to ask you what question. And when you're all done, you've basically tapped into a knowledge base that's across the board to really run down the risk. So you don't know what's going to happen when you land. You know, in the Pacific, in the Atlantic, after an abort, you're going to see different sea states, you're going to see different winds, different waves. The things we were doing in this test series was trying to put data points at these various types of scenarios so we can anchor analytical models. Then we can say, inside those actual test data points, here's what we believe is going to happen. Here's what the structure is going to do. Here's what the crew is going to do. And then our impact attenuation system, here's how it functions.
So we're talking with Mark Baldwin of Lockheed Martin. And remember to bring us your questions at Facebook via our live stream. Tell me about the best things or the worst things. I'll give you a little day. Is there a day in the life of working on the Orion?
Yeah, it's challenging and it's crazy, but it's fun. From an engineering standpoint, so I'm a biomechanical engineer. That is kind of unique. That puts me in the middle of a lot of different things. And you go into work and it's nonstop every day. There's a lot of meetings, there's a lot of analysis you have to do. It's fun because every day something new may happen that you didn't think of previously.
Right.
And it's an engineering task and a challenge to work through that. And you can't work in a vacuum. You very much have to rely on your other teammates. And that's where Lockheed Martin and NASA, we've designed this vehicle together.
Right.
This is the culmination of 3 years of planning. We wanted to do this test a long time ago, and we evolved it, and it got to the point where now everything we get out of this test is going to really build us into the future and is going to be baked into all of our vehicles going forward. Okay,
so we have a question from Rick Kaufman. What are the G-forces expected for today's test?
So it's a good question. For Exploration Flight Test 1 in 2014, we actually had sensors on board. That, if you look at the videos, that was a nominal of nominal landing, as normal as you're going to get. In that situation, we measured 3 Gs. So we had a sensor. That's just a little bit above your amusement park ride. That is not expected to cause any injury, even if you've been in space for 2 years. You know, that's one of the important aspects of our vehicle that differentiates us. We're going to be taking crew further than they've ever gone before. Spaceflight deconditioning is something we're still understanding, but it changes the physiology of the body, right? It changes the bone mineral density, it atrophies your muscles. The effect that has on whether you can withstand an impact is something that we had to account for from the very beginning. So that's part of what we're trying to understand from here is what is the severity all the way to the crew of situations like this, and then understand the loads in the body.
Right.
That's basically what we're trying to get out of all this.
So we got many people here. I failed to mention this is a NASA social event. So we have many VIPs, local, state, people, social media users that are viewing this for the first time. So we'd like to welcome them to NASA Langley. We have a question from RB Billy Bob. Why not simulate the test by computer? The current technology does not allow it.
So it turns out that I get to stand here and watch this, but I've got months and months of work to do on the computer. So we don't end with this test. This is actually the beginning of many months of effort where we analyze what's going to happen here. So imagine this. We have 530 sensors packed in there. We've run 10 tests. So we have over 5,000 channels of data, test data, that we now have to try to correlate an analytical version of what's going on here. So imagine you've got, you can't see it, but the structure in there is very complex.
Yes.
So we have structural sensors, acceleration, strain gauges, et cetera, and then we've got the seats and the dummies. We have instrumentation inside of them. We're going to analyze every bit of that because we can't go test everything that might happen out in the Pacific, out in the Atlantic in this pool. It's only so deep and it's only so long.
Yes.
Right? So this is really the anchoring data points, and we spend a lot of time analyzing cases that we can't run, but we use this test to anchor those models to make sure it actually has some physical connection to reality.
So Robert Kangas asks, how much does the Orion capsule protect astronauts from radiation exposure?
So that's something we're actually very interested in because we intend to go further out. So there are things in work. The Human Health and Performance Directorate at NASA JSC is actually doing a lot of work in radiation exposure. To be honest, that's one of the challenges that we're going to have to face. If we really want to send people to Mars, we have to make sure we understand that to the level we can. And then provide countermeasures. If we need to protect them in a new way, that's something we're going to have to certainly run to ground.
Right. We're talking with Kevin Baldwin of
Mark Baldwin.
Mark Baldwin, excuse me. So of Lockheed Martin, a crew analyst with Lockheed Martin. Kevin Massey wants to know: are one of the 9 tests covering a shallow water impact, or is there some way to completely avoid that kind of circumstance?
You can't avoid. So let me put it this way: you can bound what's going to happen, right? You don't have to account for initially landing straight upside down, right? The parachutes are going to hold you at a certain hang angle. You do have to account for wind and waves. So I get a question a lot of times, why don't we have a wave pool in here? How do you account for the fact that we're hitting flat water? Well, it turns out that when you hit a wave that's banked at a certain angle and you're coming in at a certain angle, it's the difference between those two angles that matters. And that actually has been baked into this test series. That's why we select shallow pitches, steep pitches. If you go on YouTube, you'll see some of the other tests that were actually run here. And we've run across the board. We've run cases that have dove straight to the bottom, come back upside down. We've run cases that skip out like a stone and come straight up. This one's going to be somewhere in between because we have it rolled sideways, so it's going to kind of spin out like a wakeboard almost.
Right. Cameron Putt wants to know, what is the Orion you're dropping made of?
That's a good question. A variety of things. Hold on. We're getting close.
We're getting close to the drop.
Not there yet.
Yes, we're not at 2-minute warning yet. We're not there. So we'll repeat the question that Cameron asked: what is the Orion you're dropping made of?
So a number of things. The heat shield that's on there was actually the flight test article in 2014. That is a composite skin. On the interior, you have sort of a skeleton of titanium. They're kind of like I-beams, but they're set in a pattern that's been optimized for weight. Weight is everything to try to get something into space, right? So part of the landing team, we work with the structures guys to try to minimize the weight and the size of things, but still take every load that we can possibly throw at it. So it's a combination of titanium, composite materials, aluminum, and then to get into all the details of the secondary structure, those are all very custom parts. You know, there's an army of people working on this stuff, and it's all very specific. The impact attenuation system that I mentioned underneath the seats that lowers the G's on the crew, that's a mechanism that's very uniquely designed out of still metal parts, but it's the customization of that shape and size to provide really that attenuation directly to the crew. Those are the kinds of things that we rely on specialists in our area at Lockheed Martin and NASA to help us design.
Okay. Hazim Jadala wants to ask, what is the designed diameter of Orion?
So that's a 16.5-foot heat shield. I don't know the height offhand, but Apollo was smaller than this. Our center of gravity is lower because we have a lot of stuff packed down. We have it's basically a small home, right? You have to, if you're going to take people beyond the moon, you have to be able to take all your food supplies with you. You have to take environmental control systems. So there's a lot of stuff that's packed into the vehicle. Mostly down below, we have kind of bays that you can put things in. So it's different than Apollo in that the shape and size, but the technology really is advanced, and the analysis that we can use to design the structure is really what has advanced most in the last couple of years.
So Carl Painter wants to know, has it been exposed to radiation, cold, and UV before this drop?
Not before this drop. This particular article, the pressure vessel, has gone through acoustics, which is blasting it with sound to make it start to reverberate. It's gone through vibration testing. I don't recall if we did thermal or not, because this was actually built quite a while ago. The pressure vessel part was built quite a while ago. The heat shield is relatively new. But those are the kinds of things that we have to look at prior to manned flight.
I'm Eric Gillard at NASA Langley Research Center. We're speaking with Mark Baldwin, a crew analyst at Lockheed Martin, in our run-up to the Orion water drop test. And Tim McLaughlin wants to know, are the drop tests still giving good data without the heat shield?
Well, it has the heat shield on it.
Well, I guess he's playing devil's advocate, but I think you need to have the heat shield to protect the astronauts coming to home.
Yes.
Yes.
Well, but we had a previous version of this heat shield that we took off, and we actually put the flight heat shield back on this because we really wanted to understand that structure that I described, the skin, the outer skin, and the underlying skeleton. We wanted to understand, how does the load transfer through the whole vehicle, because the heat shield really takes the brunt of the impact. Not only does it have to survive the thermal environment punching through the atmosphere, but it gets the full brunt of the landing loads. And then it has to transmit those loads through the rest of the vehicle. So that's why we wanted to actually intentionally put that heat shield on here, and we have a bunch of sensors around the heat shield itself. Now, like I said, as an analyst, we're going to take that data back and we're going to try to correlate to every section of that heat shield because every section is sized based on landing loads that we see here.
Well, my iPad just went down because it's too hot outside, so humid. So I'm just going to remember some of the questions that people asked on Facebook. So keep your questions coming.
Ask these guys.
Yeah. So what I mentioned Apollo, and there was a question that I saw was, why is the design so similar to Apollo?
So I can understand how exterior, it looks kind of the same, looks like it's a scaled up version. But you got to understand there's been many advancements in technology and you could back up even further and say, why go to a capsule again? Why are we in line with the rocket? Why aren't we repeating shuttle? Well, it turns out that all of us are developing capsules because there's an advantage to that. When you have the system stacked on top of the rocket, you can place a launch abort system somewhere in that stack that'll get you away. Orion itself, the vehicle, like I said, we've tapped into 40 years of knowledge of building satellites at Lockheed Martin. We've sent a satellite to every planet in the solar system. So there's a knowledge base there that goes beyond what they knew at Apollo. The analytical techniques that we have today, we can run terabytes and terabytes of simulations. We can run something we're modeling this at like 1 million elements to give you an idea of the complexity.
We just got the 2-minute warning ago, so we are going to, ask you one more question.
Sure.
So how has NASA Langley helped you guys out with this system?
We can't do this. This is a pretty impressive setup here. This gantry is 240 feet tall. You're picking up a 15,000 pound test article and you're swinging it at precise impact velocities and attitudes. That's something that's been here for years, and early on we, as a group, decided this is going to be the right facility. This pool didn't exist. We dug this pool just for this program, and so now we're utilizing it to get this data. They do all the data collection from the test article, and we collectively actually do the analysis. Okay. So the facility here is awesome. The guys that work it, and everybody.
I concur. I concur.
You live here.
So we're going to lay down and we're going to watch. We got the 2-minute warning. So hopefully Orion should. So Orion should be hopefully dropping down soon.
Well, do you want to know what we're seeing?
What? Yes. What we're going to. So what we're going to see? Is it going to swing, or is it going to just drop?
Okay. Yeah. So I don't know if you can see it in the camera, but it's suspended by 4 cables. Those cables and the distance it is from the pool is actually very important. We set that distance to achieve a tangential velocity, and when we drop, we're going to drop from 15 feet, and that's going to give us a normal velocity. This is going to be a 26-mile-an-hour impact. We are rolled 90 degrees away from the direction of travel, and we are pitched at 26 degrees.
T-minus 30 seconds.
That's what you're going to see. Enjoy the splash.
It's going to see a once-in-a-lifetime event, 30 seconds away from an Orion water drop test here at NASA Langley Research Center in Hampton, Virginia, on NASA's journey to Mars. This is one of the many things we have to do before humans can come down here.
12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, release.
comes the water.
That was pretty awesome. So that was one of the many things that NASA has to do in our journey to Mars. So my name is Eric Gillard of NASA Langley Research Center. I'd like to thank you so much from wherever you are watching this, all over the world. And you'd like to keep tuning into us. #NASA Social, #Journey to Mars, @NASA Langley. Thank you very much.